Hi everyone, this is Ashley Bedford, founder of the Runtime Diaries. This is day 27 of our hashtag 30 Days of Code Challenge with Educative. Today we have minimum cost to connect sticks. Let's get into this problem. Today's problem is one of the most elegant examples of a greedy algorithm paired with a min-heap. We're solving minimum cost to connect sticks, and this problem is all about understanding how future costs explode when you make the wrong greedy choice. Let's break it down. You're given a bunch of sticks. Each stick has a length. Every time you connect two sticks, it costs the sum of their lengths. After connecting them, the result becomes a new stick whose length is also the sum. The goal is simple. Connect all sticks into one final stick while spending the least possible total cost. But here's the trap. The order in which you connect them drastically changes the total price. So let's take a simple example. Sticks equals, from left to right in the array, 2, 4, and 3. First, connect the two smallest. 2 plus 3 equals 5. Now, the list becomes 4 and 5 from left to right in the array. Next, connect 4 plus 5 equals 9. Add those costs together. 5 plus 9 equals 14. That's the minimum total cost. So what happens if you connect the wrong sticks first? Imagine merging two huge sticks early on, like 10 plus 20 equals 30. That new stick of length 30 still needs to be merged again later. And that extra weight multiplies the cost of every future merge. Big merges early punish you later. The key insight is this. Always merge the two smallest sticks first. This keeps all future merges as cheap as possible. This problem is one of those pure greedy moments. You always want the cheapest operation now because that operation feeds into every future operation. So the strategy becomes pick the two smallest sticks, merge them, add the merge cost, insert the new stick back, and repeat until you have one stick left. This is the exact same pattern as Huffman coding and optimal merge patterns. Now the question becomes, how do we repeatedly pull out the smallest sticks? We need a data structure that lets us quickly extract the smallest stick, quickly extract the next smallest, and quickly insert the new merged stick. A min-heap gives us all three in O of log n time. This gives us the ideal total runtime of O of n log n. You could try the naive method. Sort the whole list every time, then merge the first two sticks. But sorting inside a loop is expensive. It turns an O of n log n problem into something closer to O of n squared log n. Way too slow. Heap or bust. Here's the actual process. First, convert the whole stick list into a min-heap. Second, initialize total underscore cost to 0. Third, while there is more than one stick left, pop the two smallest sticks, merge them, add that cost to the running total, and push the merged stick back into the heap. Fourth, when only one stick remains, we're done. The greedy choice is embedded right inside the heap mechanics. Here's the clean Python implementation. We handled the edge case where there's only one stick, which means there's nothing to connect, so we return 0. we use heapq.heapify to turn the list into a min heap. We initialize total underscore cost to 0. Then, we enter a loop that runs while there's more than one stick. Inside the loop, we use heap pop to pull the two smallest sticks, merge them, add the cost to the total, and use heap push to insert the new stick back into the heap. Finally, we return the total cost. This is the most optimal version of the solution. We get a time complexity of O of n log n because heap operations happen n times, each costing log n. The space complexity is O of n because the heap stores all the sticks. This is the best possible performance for this type of merging problem. Let's walk through another example. Sticks equals 1, 8, 3, 5. After heapify, we get 1, 3, 5, 8. Merge 1 plus 3 equals 4. Heap becomes 4, 5, 8. Merge 4 plus 5 equals 9. Heap becomes 8, 9. Merge 8 plus 9 equals 17. Heap becomes 17. The total cost equals 4 plus 9 plus 17, which equals 30. Notice how every merge is using the smallest available pair. Here's the intuition that proves the greedy strategy is optimal. Every merge stick will be used again, so sticks chosen earlier will contribute to many future merges. Therefore, the earlier a stick appears, the more important it is that it's as small as possible. By always selecting the smallest two sticks first, you avoid creating oversized sticks that snowball into massive future costs. There are some common pitfalls. First, sorting inside the loop instead of using a heap. Second, connecting large sticks too early. Third, forgetting the edge case when there's only one stick. Fourth, accidentally pushing the cost instead of the merged stick into the heap. Fifth, using a max heap by mistake instead of a min heap. And sixth, overthinking instead of using the heap pattern. Most wrong solutions boil down to ignoring the greedy rule. Smallest first, every time. Let's summarize. First, always merge the two smallest sticks. Second, min heap gives optimal efficiency. Third, the cost model encourages greedy behavior. Fourth, this mirrors Huffman coding and optimal merge algorithms. And fifth, final runtime is O of n log n and very scalable. This is a perfect example of picking the right tool, the heap, to express the greedy insight. And that's a wrap for day 27 of our hashtag 30 Days of Code challenge with Educative. If you like this video, like it down below, share it with a friend, and subscribe to our YouTube channel. We hope to see you next time. Bye.